Pluto had it coming from the beginning. It was like it never really belonged. Pluto's orbit crosses that of another planet. That's no kind of behavior for a planet. Pluto and Neptune, two of the most enigmatic and distant bodies in our solar system, have always danced in a celestial ballet defined by gravity, distance, and time. Locked in a delicate orbital resonance, Pluto has always avoided a direct collision with Neptune. Even though their paths appear to cross when viewed in two dimensions, this protective orbital arrangement has persisted for millions of years, a cosmic choreography that astronomers once believed unbreakable. But now, recent scientific discussions have explored hypothetical scenarios challenging this stability. No collision between Pluto and Neptune has occurred, as confirmed by current astronomical data. But theoretical models suggest potential disruptions could have significant consequences. And what's unfolding in these models isn't just astonishing, it's thought-provoking. To stay updated on the latest space discoveries, engage with trusted science channels, and share your thoughts in the comments below. The very idea that Pluto and Neptune could collide shakes the foundations of what was thought to be understood about orbital mechanics. These two celestial bodies have long maintained a 3-to-2 resonance, meaning that for every 3 orbits, Neptune completes around the Sun, Pluto completes 2. This locked rhythm has kept them safe from each other for eons, despite the fact that their orbits intersect. But hypothetical scenarios suggest something could go wrong. Something monumental could shift this ancient balance. For such a collision to occur, it would require a massive perturbation, an unseen force or influence powerful enough to disrupt what was once considered a gravitational constant. This hypothetical event is not a simple fender bender between two frozen lonely orbs in the outer solar system. A planetary scale collision, if it were to happen, especially one involving Neptune, a gas giant, and Pluto, a dwarf planet made of rock and ice, would unleash forces far beyond comprehension. The energy released in such an impact would rival the magnitude of planetary formation events. Temperatures would spike in the millions of degrees, instantly vaporizing materials and sending shock waves of debris spiraling outward into the Kuiper Belt. This wouldn't just be a plume of dust. This would be a curtain of chaos sweeping across the outer solar system. At the heart of this theoretical collision is a sobering implication that our solar system could be far more dynamic and unstable than previously thought. If Neptune's orbit could be altered even slightly enough to bring it directly into Pluto's path, then no planet is truly safe from orbital interference. It raises important questions about the potential existence of an external force, perhaps a rogue planet or a massive object previously undetected that could influence the outer solar system. Could this be related to the first observable consequence of Planet 9, the hypothetical massive body thought to lurk far beyond Neptune? Or is it something even more unfamiliar, like a theoretical passing black hole or gravitational shock wave from outside the solar neighborhood? The hypothetical collision itself would not be a clean smash. It would be more like a catastrophic melding of two profoundly different planetary structures. Neptune, composed primarily of hydrogen, helium, and ices like water and ammonia, would be pierced by Pluto's dense icy core like a spear of frozen rock. The result wouldn't be total obliteration, but transformation. The atmosphere of Neptune would be visibly disrupted, torn into turbulent streams of violent storms and energy vortices. Massive gaps would form in its cloud tops, revealing layers of unusual heat and light beneath. These anomalies would be unlike anything observed before in planetary atmospheres. Meanwhile, fragments of Pluto would be cast off, some large enough to be moon-sized. These new celestial shards would race across the outer solar system, trailing unpredictable paths. They would pose immediate risks to other Kuiper Belt objects, many of which are only loosely held together by gravity. The Kuiper Belt itself, already a frontier of instability, would become a war zone of colliding debris, radiation bursts, and gravitational echo effects. Entire generations of comets and icy bodies would be flung inward toward the sun. Some could eventually enter the inner solar system, potentially bombarding the planets with a sudden uptick in high-velocity impacts. The electromagnetic ripple from this theoretical event would begin reaching beyond its origin. Planetary magnetospheres would respond in odd ways. Uranus and Saturn would show spikes in magnetic readings as if resonating with some deep space disturbance. Earth-based telescopes and satellites would capture anomalous signals in the radio and infrared spectra. Waves of radiation that are irregular, pulsing, and growing stronger. These could be evidence of molecular chaos erupting from the hypothetical collision site, or, potentially, signs that space-time distortions might begin to propagate. Then would come the gravitational lensing. Tiny but measurable warps in space detected as light from distant stars passes through the zone of impact. These distortions would hint that the mass of the Pluto-Neptune event had condensed into something far more compact and energetic than two mere planets colliding. Some physicists speculate that a proto-singularity could form, a dense knot of matter and energy so immense that it might become a localized gravitational well, perhaps the beginning of a new type of object in our solar system, something between a neutron star and a black hole. If such a formation were to continue, the ripple effects would threaten not just planetary orbits, but the very curvature of space in this quadrant of the solar system. The ripple effects wouldn't be limited to gravity. There would be chemical and atmospheric consequences as well. Spectral analysis from remote observatories would show sudden releases of ammonia, methane, and more complex organic compounds. These gases would rapidly expand into the surrounding space, forming colorful, luminescent plumes that twist like auroras in the void. While beautiful, these emissions would be filled with high-energy particles capable of damaging spacecraft, distorting sensors, and perhaps interfering with deep space communications. The solar wind would also begin reacting to the surge of particles and energy emanating from the hypothetical impact. Streams of charged ions would be deflected, redirected, and in some cases accelerated toward the inner solar system. As they interacted with the heliosphere, the boundary that separates solar influence from interstellar space, odd patterns would emerge. Instruments monitoring the heliospheric sheath would report spikes in pressure and temperature, as though the shock of the Pluto-Neptune event were altering the boundary layers of our solar system itself. Perhaps most intriguing of all is the potential effect on time measurements. Atomic clocks on board probes near the outer planets might begin showing microscopic drifts, barely perceptible, yet real. These time anomalies could point to slight variations in the fabric of space-time itself, a warping initiated by the sheer force and density of the theoretical impact. If space-time were twisted, even subtly, then relativistic effects might begin to distort how we perceive and measure motion, duration, and distance in that region. The question of what could cause this once impossible event would hang over everything like a sword. Natural perturbations over millions of years don't explain a potential sudden breakdown in orbital harmony. It would imply something immediate and violent. Could it be a rogue object, unseen until now, that barreled through the Kuiper belt and nudged Pluto just enough to set this fate in motion? Could Neptune itself be perturbed by an external gravitational influence? Or is this an early symptom of a far larger cosmic shift potentially affecting not just our solar system, but possibly others nearby? Some theorists are speculating about gravitational waves from outside the Milky Way, ancient echoes from merging black holes or collapsed galaxies that could eventually reach us. Others believe this could be a result of dark matter clumping more densely in certain regions, enough to shift the trajectories of outer solar system bodies. Still, others consider whether humanity's understanding of celestial mechanics is incomplete or based on faulty assumptions about long-term orbital stability. What is certain is that this theoretical event would change everything. The solar system, once thought to be a relatively static environment on human timescales, could prove itself to be volatile and unpredictable. The stability we've taken for granted, from the slow progression of seasons on Earth to the predictability of planetary movements, would be in question. If such a collision could happen once, it could happen again. And not just in the far reaches of space. Inner planets, including Earth, could one day experience the gravitational aftershocks. The potential consequences go beyond physical destruction. This hypothetical collision raises philosophical and existential questions about our place in the cosmos. If planets could collide in what was once considered a safe zone, what other dangers have we overlooked in our assumptions about the universe? Are we living in a window of calm between storms, unaware of the chaotic energy bubbling beneath the surface of what we call cosmic order? The simulated data from such a scenario would be unprecedented. Images, energy readings, mass estimates, all pointing toward a singular truth. The solar system could awaken to a new era. The silence of space would no longer be serene. It would be charged, electrified by the violence of planetary death and the birth of something entirely unknown. The fabric of our cosmic neighborhood would be torn. And what lies beyond that rupture remains shrouded in both beauty and mystery. This is not merely a theoretical collision. It is a cosmic thought experiment. The solar system would speak in the language of mass, gravity, and light. And what it says is clear. The age of predictable orbits and quiet skies could come to an end. As the simulated impact site continues to glow, pulse, and throw off waves of matter and energy, humanity would be left to reckon with the reality that we are far from being spectators. We are participants in a celestial story that is still being written, with chapters darker and stranger than we ever imagined. The rupture left behind by Pluto's hypothetical collision with Neptune would no longer be confined to isolated damage in the distant reaches of our solar system. It would start to act like a wound in the fabric of our planetary neighborhood, leaking gravitational noise, atmospheric anomalies, and electromagnetic echoes into areas previously untouched. What was once a specific event would rapidly expand into a dynamic process of disruption. And now, the very boundaries between order and chaos in the solar system would begin to blur. As telescopic networks around the globe pivot toward the theoretical region of the collision, a clearer picture begins to emerge, not of aftermath, but of evolution. The post-impact structure would defy previous models. Neptune, while still partially intact, would no longer resemble the gas giant we once knew. Its once uniform bands of bluish clouds would devolve into a maelstrom of swirling layers with patches of darkness that absorbed nearly all visible light. At the center of these dark vortices, energy emissions would intensify. These areas would behave like heat engines, radiating in unexpected frequencies across the electromagnetic spectrum, suggesting processes taking place that have no precedent in planetary physics. A secondary structure would begin to coalesce within the upper atmosphere of Neptune. Initially thought to be nothing more than lingering debris or post-collision turbulence, this formation would appear to be gravitationally self-contained. It would spin independently within Neptune's gaseous envelope, forming a core within a core, a nested object that resists classification. Its mass would continue to grow, drawing in both atmospheric gases and fragments of Pluto that orbit in chaotic paths. There would be rising concern that this nested mass could represent the early stages of an artificial gravity well, a kind of embryonic body forming under conditions not seen since the era of planetary birth. Scientists might begin referring to it informally as a chaos phage, a structure born out of destruction that seems to feed off entropy itself. It would rotate at irregular speeds, and telemetry from probes would indicate variable mass density that changes from one moment to the next. The data implies it's not a solid object in the traditional sense, but a cluster of unstable energies coalescing into physicality through unknown mechanisms. If this were accurate, it might be the first known object in the solar system that doesn't obey Newtonian gravitational constants in full, but responds to space-time warping like exotic matter theorized in quantum field equations. This chaos phage would begin affecting Neptune's magnetic field, which would pulse erratically and project tendrils of electromagnetic distortion thousands of kilometers into space. These distortions would reach out like skeletal arms, interacting with solar radiation and distorting signals from distant space observatories. In some regions, they would act like lenses, focusing light in ways that make stars appear to blink or shift position. In others, they would scatter signals entirely, making regions of space go momentarily dark in every observable frequency. Not all changes would be electromagnetic. New orbital objects, previously cataloged and stable, would experience unexplained velocity changes. Dwarf planets like Haumea and Makemake, once peacefully orbiting far from the hypothetical collision zone, would be pulled into slow spirals that bring them gradually inward. These wouldn't be gravitational tugs from a nearby planet. They would be coherent vectors of force pointing not toward Neptune itself, but toward the developing chaos phage inside its disrupted core. The emerging object might form a gravity well distinct from Neptune's original center of mass, which implies the creation of an entirely new orbital attractor, a rogue anchor in our solar system's architecture. Farther out, the Kuiper belt would begin to unravel. Long-held assumptions about its structure would fall apart. Asteroids, once classified as cold classical bodies believed to be among the oldest and most undisturbed, would be flung into new paths. Their motions would no longer match their projected ephemerides, and several would begin crossing into trajectories that arc toward the inner planets. If enough of these icy remnants became destabilized, they could establish a corridor of debris, an interplanetary conveyor belt funneling fragments across the solar system. A more concerning phenomenon would be the increase in interplanetary plasma density. The solar system, though seemingly empty, is filled with diffuse gases and charged particles moving in solar wind patterns. In a simulated scenario, the density of this plasma would triple in areas adjacent to the Neptune-Pluto impact. No known solar event would explain this. It would point instead to a release of subatomic material from deep within the impacted planets, stuff buried under frozen crusts and held in molecular stillness for billions of years, now suddenly freed into motion. Among the byproducts emerging would be unstable isotopes, many of which are unknown to Earth-based nuclear science. Mass spectrometry from deep space observatories would identify transient elements, short-lived, rapidly decaying materials that shine for seconds before vanishing. These exotic isotopes shouldn't exist in nature. They are the kinds of things theorized to emerge only under conditions similar to particle accelerator collisions or stellar cores. That they're being produced in this scenario suggests the impact would trigger a sustained process of nucleosynthesis, the building of new elements from the wreckage of old planets. And then there is the light. Observers at high altitudes and polar regions on Earth would begin to detect bizarre visual phenomena. Not auroras, but radial sky patterns, rings and flares, and spectral bands that shouldn't even reach Earth's atmosphere. Some would resemble structured light pulses shifting in regular intervals, as though encoded. They wouldn't resemble any known communication signal, but their uniformity would be too precise to be random. Some physicists might argue these are simply resonant echoes of the electromagnetic chaos unleashed by the theoretical impact. Others might entertain a far stranger hypothesis that the collision triggered a quantum cascade of energy, detectable across vast distances and possibly even across dimensions. In the solar system's deep field, the Oort cloud has remained an icy mystery for centuries. But recent remote sensing in this scenario would reveal thermal spikes from that region, sudden outbursts of warmth and motion in an area that should remain near absolute zero. Cometary bodies would be disturbed, their pristine equilibrium, undisturbed since the solar system's formation, would break down. Some comets would heat and fragment, others accelerating toward the sun, leaving brilliant and irregular tails behind them. The timing of these movements would link too closely to the theoretical collision to be coincidental. It suggests that the entire solar system, even its most remote regions, would resonate like a bell struck by a cosmic hammer. Communication systems across deep space missions would start to degrade. Probes positioned to monitor outer planetary activity would go silent one by one. Their data streams would fill with noise and static before falling dark entirely. It's not that they would be destroyed. Telemetry would show them intact, but they would no longer orient or communicate. Their gyroscopes would spin out of alignment. Their star trackers would show false positions, and their onboard clocks would drift beyond the limits of correction. It's as though their position in space had shifted without movement, a conceptual displacement rather than a physical one. That would lead to the most radical theory of all, space-time displacement. Quantum physicists analyzing data from the hypothetical impact zone would believe we might be witnessing the emergence of a localized space-time rupture. Something that began with gravitational shock waves and evolved into a standing wave phenomenon. A fold in space might develop where time and distance behave differently. Light speed delay measurements, typically reliable to the microsecond, would vary unpredictably. Lasers fired across known distances would no longer return at expected intervals. If this continues, The region near Neptune might become unreachable, not due to distance, but due to topological separation. It might become another kind of space entirely. Whether this rupture is naturally decaying or self-sustaining remains unknown. But if the latter were true, we might be observing the solar system's first indigenous singularity, an object born not from stellar collapse, but from planetary collision, creating a new kind of space-time disruption entirely unaccounted for by standard models of cosmic evolution. On Earth, the psychological and sociological ripples would begin. Though the event lies billions of kilometers away, its theoretical implications would touch everything. Governments would race to decode what this means for planetary defense strategies. If distant collisions could lead to unpredictable gravitation or radiation spikes, what safety exists for Earth from less stable regions of the cosmos? The sense of security long held by humanity, rooted in the assumption of orbital regularity and solar constancy, would crack. For the first time in modern history, people would need to consider the solar system not as a static environment, but as a volatile system full of dormant potential threats. Tensions would rise among global scientific institutions. Competing theories, some bordering on metaphysics, would emerge. One faction might believe this collision is evidence of a cyclical cataclysm, an event that happens every few 100 million years and resets the dynamics of our solar system. They would point to geological evidence of mass extinctions and magnetic reversals as potential markers of past resonant disruptions. Another group might argue this is an artificial event, the result of manipulation, either by advanced intelligences or unknown cosmic mechanisms not yet understood. Astrobiologists would discuss the idea that such events might be the triggers for planetary evolution on a biological scale. If Earth were to experience a similar transformation, the resulting energy and radiation bursts could act as catalysts for mutation and accelerated evolution or extinction. The role of celestial violence in shaping life's trajectory would be re-examined in light of this theoretical and speculative example. Even the sun would start to respond. Solar flare patterns would become erratic. The heliospheric current sheet, an enormous structure of magnetic influence generated by the sun, would show signs of being twisted or pulled. Heliosysmology data used to monitor the sun's interior oscillations would return patterns that hint at subtle, deep changes in the solar core's behavior. These alterations might be minor and temporary, or they could be signs that the internal rhythms of the sun itself are beginning to synchronize with the new distortions developing across the solar system. There is no certainty left, only observation and reaction. The next generation of telescopes, probes, and particle detectors would be rushed into development. Missions once planned for leisurely exploration of outer planets would be retasked for emergency mapping of gravitational flux. Deep space beacons would be recalibrated. The hunt for Planet 9 has taken on a new urgency as scientists seek to determine whether it could play a role in such a catastrophe, or if it too would be affected by what might occur. What's theoretically forming in the outer solar system is not just a new structure. It's a new frontier, a place where known laws might break, where traditional science starts to unravel, and where the familiar motions of planetary dance give way to something more ancient, more primal. The hypothetical collision would not simply alter the orbits of distant planets. It would carve a wound into the solar system's symmetry, one that might not close for eons. And whatever emerges from that wound may change not only the shape of our solar system, but the way we understand the universe itself. As the echoes of the Pluto-Neptune theoretical collision continue to reverberate across the solar system, the consequences would take on increasingly multidimensional characteristics. The most intriguing realization among astrophysicists and cosmologists is that the solar system's architecture, once considered a static masterpiece of gravitational harmony, may have always been a fragile balance, a temporary lull in a broader, wilder cosmic process potentially erupting into visibility. Each new simulated data stream from such a scenario would add another layer of complexity, pointing not just to the scale of the event, but to the radical transformations it would unleash at multiple levels of physical reality. Newly deployed deep spectrum imaging tools aimed at the theoretical impact region would capture anomalies that cannot be accounted for by current models of planetary behavior. Instead of merely detecting increased thermal radiation or ionized gas flows, instruments would pick up structured energy configurations, geometric patterns forming in plasma clouds that remain coherent far longer than expected. These wouldn't be random turbulence or chaotic interactions. The patterns would resemble fractal geometries, self-replicating and evolving, hinting at deeper forces at work. They wouldn't act like the results of a collision. They would behave more like signals, messages etched into the flow of energized matter. These formations would evolve over time, splitting, reforming, and shifting frequencies in a coordinated manner. If this were a natural process, it might represent a class of cosmic behavior yet to be observed, energy organizing itself spontaneously into self-replicating structures as a response to extreme pressure gradients. If it's not natural, then it raises the speculative possibility that the impact zone could be influenced by intelligent processes or might catalyze the emergence of behavior that mimics life or cognition at a plasma field level. In either case, the region would demand an interdisciplinary analysis that spans astrophysics, quantum mechanics, information theory, and even biology. Another concerning revelation would be the apparent breakdown of Newtonian predictability in orbital behaviors near the theoretical impact zone. Several probes sent to monitor the gravitational changes would be observed to alter course mid-transit without application of thrust. These wouldn't be malfunctions. They're navigational anomalies that suggest they are moving through regions of warped space where linear motion produces nonlinear displacement. The effect would not be uniform. Some probes would speed up, others slow down, and some curve unpredictably, as if they're being influenced by hidden fields or gravitational eddies invisible to conventional instruments. These spatial deformations suggest that the region would no longer operate under the standard curvature of spacetime. Instead, space itself would behave like a dynamic semi-fluid medium, stretching, twisting, and compressing in localized zones that obey a new geometry. The foundational assumption that the solar system exists in a smooth gravitational gradient around the sun would collapse. Instead, it would become increasingly evident that multiple gravitational knots may exist where objects behave differently depending on their mass, speed, and composition. This would be a departure from general relativity. And while it doesn't invalidate Einstein's equations, it may signal that the extreme energy concentration caused by the theoretical collision has invoked higher-order curvature effects predicted only in theoretical physics. In parallel, deep-sea neutrino detectors on Earth, typically used to monitor high-energy particles from space, would report a sudden increase